Let's discuss the fundamental theorem of calculus for line integrals. If you're computing the line integral for a vector field f, which is conservative, that is, f equals the gradient of some scalar field, if you're computing the line integral of f over some trajectory or path, some parameterization c, you can just take the values of the potential function, the scalar field, at the end point of the trajectory, the beginning, the initial point of the trajectory, and subtract them. So you can see right away why this is called the fundamental theorem of calculus, because it's just f of b minus f of a in the old-fashioned sense, except things have gotten a little more complicated now. This works in 2 or 3 dimensions. C is a parameterized path from A to B. A couple of things are pretty obvious now. If f is a gradient field, if it is conservative, and if you go from B to A, you're just going to reverse these, so they'll change the sign. Some people like to write C star for the reverse, and in that case, you'd say, well, if you use the path C star instead and do f dot dr, you're just going to get the opposite, the negative, of the original, because you're just reversing A and B. Another thing, and here's some notation you might not have seen before, the circle on the integral sign means closed path. If C is a closed path, and again, f is conservative, this isn't true if f isn't a conservative field, you just get 0, because B and A are the same point, so you end up where you started from, and this is the line integral of a conservative field over a closed path, and that gives you 0, which is going to remind you about how work done in a gravitational field comes out to be 0 if you end up where you started from. That's part of what's going on here. Let's look at an actual example using a problem that we looked at before. Let's suppose, just for fun, that our field, 3-dimensional, f of x, y, z, is equal to 2x plus 2y for my first component, 2x plus 2yz for my second component, and y squared minus 6z for my third component. Now, as you may recall, we found out that f equals the gradient of f, where f of x, y, z, our potential function, turned out to be x squared plus 2xy plus y squared z minus 3z squared. Let's hang on to that for a moment, okay? I want to talk about the line integral over C of f dot dr, where we're in 3 dimensions. And let's say I'm going to start here at 1, 0, 0 on the x-axis, okay? And let's suppose we have a helix for our trajectory. And the helix is going to go around just once until it reaches the point 1, 0, 2. If you're wondering what kind of trajectory would give this sort of result, well, let's just do r of t, where we have cosine t, sine t, that gets us going around in the circular motion, and finally t over pi. And let's let t go from 0 to 2 pi. You can check fairly quickly that this is going to start us off at 1, 0, 0 and move us around in a helical arc until we get to 1, 0, 2. All right? Now, of course, we now have the following situation. We are talking about first component 2x plus 2y with respect to x, second component 2x plus 2yz with respect to y, and the third component y squared minus 6z dz. Isn't that a lovely line integral to evaluate? Of course, from our parameterization up here, we know that x is cosine t, so dx is just minus sine t dt. We know that y is sine t. You always get your parameterization substitution from your curve parameter. And let's see, dy cosine t dt. And last, z is t over pi, so dz is 1 over pi dt. If we didn't have the fundamental theorem, and if we didn't have our potential function up there, we would now be doing a massive amount of substitution. Feel free to go ahead and check this to make sure it works. I'm not going to do that. Instead, I'm going to use the fundamental theorem of calculus for line integrals, and that implies that my integral is x squared plus 2xy plus y squared z minus 3z squared, evaluated from my initial point 1, 0, 0 to my terminal point of 1, 0, 2, courtesy of the fundamental theorem of calculus for line integrals. So what happens? Well, plug in 1, 0, 2, you get 1 plus 0 plus 0 minus, plugging in a 2 here, 12 minus 1 plus 0 plus 0 minus 0. Put it all together. The ones cancel. Minus 12. Okay? So our result for this integral is minus 12. I certainly prefer the fundamental theorem of line integrals to doing a massive amount of substitution with parameterization in order to evaluate this. But I want to point something else out. Fundamental theorem tells us that only the values of the potential function at the endpoints matter. So if you had another path that started here and ended there, you should get the same result. In fact, if I replaced the helix with a straight line path that goes from here up to there, that would work. Let's find out what that would be. R of t, I'll call this R1 because this is a new parameterization, not to be confused with the helix. And let's see, x is always 1. Okay, y is always 0. And z is the only one that varies, so let's call it t. And z, or t in this case, goes from 0 at the bottom to 2 at the top. So what happens on this new path, I'll call him C1 to correspond with the index on our new parameterization, f dot dr. Okay, I'm not using the fundamental theorem of line integrals this time directly. I'm looking at this expanded version of my line integral. Let's see. Because x is a constant, dx is 0. So I'm looking at 0. Because y is a constant, dy is 0. So my second term is 0. My third term, y squared, is, it's still 0, minus 6t. And And dz, well, z is t, so that's dt. Zero to 2. I am computing the integral from 0 to 2 of minus 6t dt. Okay, what happens? T squared over 2, I get minus 3. T squared from 0 to 2. Evaluate that. Minus 12, which is exactly the result we got from using the fundamental theorem of calculus for line integrals. That's fairly interesting information. You can either parameterize and substitute, or if you have a conservative field and you know what the potential is, you can substitute and evaluate at the endpoints and subtract. Or if you'd rather simply replace your complicated curve with a simpler curve, you can do that too.